Hello, my name is Dr. Richard Head, and I'm going to talk to you today about the universe. The universe is big. We know this because we can observe things which are a really long way away, and then some. And then we can see things beyond them. And then we can see things beyond them. And beyond them. And, well, you get the idea. This photo, the Hubble Ultra Deep Field image, is of a very small part of relatively dark sky, 1/26,000,000th of the whole sky, and yet it contains approximately 10,000 galaxies. Are you feeling small yet? Also, the universe is getting bigger. We know this because things are moving away from us, and the further away they are, the faster they are moving away. It's a bit like having dots on the surface of a balloon and blowing it up. Not that sort of blowing up. That's better. Now, if the universe is getting bigger, then in the past it was smaller, and in the distant past it was very small. At a best guess, we think the universe began, that is, was at its smallest, between 13 to 14 billion years ago. We also have to consider the shape of the universe. Is it flat or curved? Some people think the universe is so curved it wraps back on itself. Some people even think it is shaped like a torus. Not that sort of torus. That's better. But why would the universe be curved at all? To understand that, we have to go back to a rather bright German-born student of physics who was working in a patent office in Bern. Clearly, he had a lot of time on his hands at the patent office, because in 1905 he published 4 papers, one of which... I'm getting ahead of myself. Let's go back to the 1800s. The work of Faraday and Maxwell had led to the conclusion that light was an electromagnetic wave, and in 1887 Albert Michelson and Edward Morley performed an experiment, imaginatively known as the Michelson-Morley experiment, which showed the speed of light, known as c, was always the same, regardless of the speed and direction of movement of the observer, a conclusion many people thought was a load of tosh. Now, back to our unnamed patent clerk. He asked a simple question. What if this is not nonsense? What if light really does have this magical property? Well, he did some maths and came up with some interesting conclusions. For a start, space and time are not separate entities, but both form part of 4-dimensional space-time, and energy and matter are different forms of the same thing, which had rather unfortunate consequences. Now, imagine you drop something small and heavy. The item will accelerate due to gravity. The rate of acceleration is roughly 9.81 meters per second squared, which we call g. And we all know what it is like when we sit in a car which is accelerating. It feels like we are being pushed back into the seat. And if the car accelerates at roughly 9.81 meters per second squared, g, it feels equivalent to gravity. The same would happen in a spaceship. If the spaceship were to accelerate at g, then we would be pushed into the back of the spaceship, and it would feel like gravity on Earth. So, acceleration and gravity feel the same. Maybe other aspects of them also appear the same. Imagine this spaceship is not moving, and it has windows on both sides, and a torch is shone through it, and you can see the beam of light. I think someone needs to dust in this spaceship. Now, make the spaceship move. As the light travels from one side to the other, it gets closer to the back of the ship. From inside the ship, it appears to travel diagonally. And if the spaceship is accelerating, from inside the ship, the light appears to follow a curved path. But light travels in a straight line. So, if it is curving, the obvious explanation is that it is travelling in a straight line through curved space, which means acceleration is curving space, which means gravity, which is equivalent to acceleration, will also curve space. Actually, remember the bit a while back about four-dimensional space-time? Cue a bit more very complex maths by the unnamed patent clerk, and we get what is known as general relativity. And this gives us various odd effects. For example, clocks run at different rates depending upon their relative speeds, or the intensity of gravity to which they are subjected. Or massive objects bend the light passing them, so objects don't appear to be where you think they should be. And all of this has been confirmed by experimentation and observation. The greater the density of mass energy, the greater the effect is. Now, the densest observable object in the universe is a neutron star. 1 cubic centimetre weighs approximately 100 million kilograms. That's about the same as 8,850 cubic metres of lead, or 41,600 cubic metres of concrete, or the heads of 20 million very dense people. But even a neutron star is surrounded by a lot of empty space, so the mass energy density of the universe is very much lower than this. But go back 13 or 14 billion years, the universe was very small, but still had all the same stuff in it. So back then, the mass energy density must have been very high. So that must have had an unimaginable impact on the curvature of space-time, and the slowing down of time must tend towards stopped. So, we don't really have any concept of before the universe began. We don't know why it began, what shape it really is, nor how it will end. And is that altogether surprising? Asking a human to describe the universe is like asking an ant to explain Pluto. Or, to put it in universal terms, all humans are very dense. Thank you.